All right, now we're connected. And jumping back into Hess's law reactions. So Hess's law lets us use, let's go back to the slides. When we are doing the heat of a reaction or enthalpy change of a reaction, if our reaction changes, then our heat of the reaction will also change. So if a chemical equation that we've got a heat of reaction for is multiplied by some factor, we're going to multiply the heat of reaction by the same factor. So we can double it. That would double all the coefficients in our reaction, and it would also double our heat of the reaction. We can also reverse the chemical equation, and that's going to flip our heat of reaction from positive to negative or negative to positive. And then the Hess's law part is that we can add those chemical equations together. So like in this example, we've got A plus 2B going to C and C going to 2D. If we add these together, we add up both sides, we see that we've got C on both sides. The C's will cancel out because they're on both sides. And we're left with everything on the left going to everything on the right. We add up the delta H values, and we get the new heat of reaction for our added steps. And we did some ideas thinking about this, and also an example. And now we've got this example that we left off with last time. So we want to find the heat of reaction for this reaction. 3 hydrogen gas plus ozone going to 3H2O. So we've got O3 here. This is not O2. It's O3. And we've only got 2 reactions to work with this time, so it's, I would say, a fair bit simpler than our other example. We have H2 on the left and H2O on the right. Those both show up in our first reaction, but our coefficients, we'll notice, we've got a coefficient of 2 in front of our H2 and in front of our H2O. To get that up to 3, we would need to multiply by 1.5. So then we'll have 3H2 plus 1.5 O2 going to 3H2O. The 1.5 is also going to multiply by our delta H for our first reaction. And then our second reaction, we've got O2 going to O3. We need O3 on the left side, and it's currently on the right side, and so we're going to have to flip our second reaction. So that's multiplying our delta H by a -1. And then we'll have 2O3 going to 3O2. So from our changed first reaction, we have O2 on the left side. From our changed second reaction, we've got O2 on the right side. We've got 3O2 in our second reaction. We've got 1.5 O2 in our first reaction. Our coefficients on H2 and H2O are correct in our first one, so that means we're going to adjust our second reaction to get the 3O2 to match the 1.5 O2. So we're going to flip it. We're also going to multiply it 1/2. So we'll have O3, which is ozone, going to 1.5 O2, and then we'll add these together. So hopefully we can see the 1.5 O2 on the right side, the 1.5 O2 on the left side. Those will cancel out. We'll be left with 3H2 plus O3 goes to 3H2O, and that's the reaction that we wanted. Then we have to do our transformations for our delta H values to calculate what this final H value is going to be. So for our first reaction, we multiplied it by 1.5. For our second one, We flipped it, which means we multiplied it by -1. We also multiplied it by 1/2 or divided it by 2. So it's going to be a negative 285.4 over 2 kilojoules. And it looks kind of funky the way that I wrote it out. So negative 483.6 times 1.5. This top part is negative 725.4 units of kilojoules that are cut off. And our second one, negative 285.4 divided by 2, negative 142.7, also kilojoules. Add those together, and our overall for our delta H should be negative 868.1 kilojoules. Questions or confusions? Great. So our delta H we can measure experimentally by doing calorimetry, either constant volume or constant pressure, coffee cup calorimetry, or by inference through Hess's law by adding up a sequence of steps. We can also calculate a delta H from standard enthalpies of formation. So we're going to look at some tables in a bit here that show us standard enthalpies of formation. Because delta H is a change in enthalpy, since it's a change, that means that we need some reference state. So we can define a convenient reference state, a convenient 0 value for whatever is convenient. For changes in altitude, our changes in altitude we measure relative to sea level, generally. So like our altitude is measured reference sea level. We're like 400 feet above sea level. It's convenient because there's sea level not everywhere, but lots of places all over the world, and so it's relatively easy to measure relative to sea level. If everything was relative to the bean in Millennium Park in Chicago, that would be very inconvenient because the bean in Millennium Park in Chicago is only in one place. So it'd be hard for somebody in Abu Dhabi to measure their elevation relative to that giant looking shiny bean thing in Chicago versus sea level. We also can measure changes in enthalpy relative to enthalpies of pure elements in their standard states. So we're going to learn about standard states and enthalpy changes. So 1, the standard state. Standard state is typically values that are 1. So this is the state that we're defining as our base or reference state. For things that are gases, it's the pure gas at 1 atmosphere of pressure. So pure gas, 1 atmosphere of pressure. For a liquid or solid, it's the pure substance in its most stable form. Typically the form that we find it, the natural, quote unquote natural form, at 1 atmosphere of pressure, and the temperature is usually specified. It should always be specified when you see it in a table. But typically it's probably going to be room temperature, so 25 degrees Celsius. For a substance that's dissolved in a solution, it's 1 molar. So standard state is basically the pure substance at 1 atmosphere, or 1 molar concentration, so 1 mole per liter concentration if it's dissolved. Our standard enthalpy change is the enthalpy change when all of the reactants and the products are in their standard states. The degree sign indicates standard. The plimsoll is the name for that. So this little zero that we're adding, zero looking thing that we're adding, the degree sign, that means that we're talking about standard state. The standard enthalpy of formation, so standard because we've got the little zero looking thing in the top right corner, enthalpy because it's H, of formation because we've got the subscripted F. This is the enthalpy change for the reaction forming 1 mole from its constituent elements. We can also call this the standard heat of formation, where H here might stand for heat. For standard enthalpy of formation, the elements must be in their standard states. I think aluminum, we would be specifying that it's a solid. Sometimes there's more little labels that they have after them. So the elements have to be in their standard states. That's going to be all of our reaction side, or reactant side. Our product side is going to be 1 mole of our product. So forming 1 mole of product from constituent elements. For pure elements that are in their standard states, because that's their normal naturally occurring state, we've defined that as the 0. That's the state that we find them in. And so they have a heat of formation, standard heat of formation, of 0 kilojoules per mole. And we've got our first of 2 tables that we'll be seeing today in this lecture. So this is what a standard heat of formation table might look like. Notice that it's specifying the temperature, so we don't really have to worry about the temperature. It's also not something that we would have to worry about anyway. And the way that these tables are typically laid out is by atom or by element in alphabetical order. So it's not going to be labeled like everything is listed in there however many times. So generally we're looking for things that aren't hydrogen. I've pointed out sodium chloride here because we'll be using this one later. So you don't have to memorize standard heat of formation. I just pointed it out because we're going to use it in an example later. So if you're watching the recording, maybe write that down or mark this spot to come back to. So this sodium chloride, negative 411.2. Notice that some of these have 0 values. These 0 values mean that these are all the standard states. So these 0 values, these are our standard states. Those are important because for a standard heat of formation, those are the ones that we're going to be putting on the left side, the reactant side. So if you're not sure what the standard state of something is, if you've got one of these tables, you can go back to the table, find the ones with zeros in them. Those are what you're going to be putting on the reactant side. And we'll show you how to do that. I'll show you how to do that in a bit. Okay, so standard enthalpy of formation for methane. We've got carbon as a solid as graphite rather than as a diamond, plus 2 hydrogen as a gas, going to CH4 also as a gas, and this is our delta H of formation value for that standard state process. Formation reactions are a little bit weird, or can be a little bit weird. We're combining elements in their standard states. Elements in their standard states to form 1 mole. So we're always going to set our product side to have a coefficient of 1. And this can lead to us having some things that look illegal. If you're not sure what the standard state is, you can find that form from one of the appendices or from a table, the one that's got a heat of formation, standard heat of formation of 0. Because our definition requires that 1 mole of compound be made, the coefficients of the reactants may be fractions. This is the only time, other than briefly for Hess's law, this is the only other time where we might see fractions for coefficients, and it's okay. And then the units of our delta H, our standard delta H of F, standard heat of formation becomes kilojoules per mole because the reaction is always written for 1 mole of product. So if we want to write a formation reaction for carbon monoxide as a gas, for CO as a gas, the two elements that we have are carbon and oxygen. And so we're going to just write out the elements, just what they are, and then we'll work out what are their standard states and what are the coefficients that they need to have. So we're starting with just carbon and oxygen. Those aren't their standard states, and so we have to figure out what their standard states are. There's a couple of forms of solid carbon. The one with a 0 for the standard heat of formation is graphite. Oxygen standard state is O2. So it's O2 as a gas. So those are the reactants. So we go from just the elements to their standard states. And then we also have to make sure that it's balanced, because currently we've got 1 carbon on both sides. That's good. We've got 2 oxygens on the left side, 1 oxygen on the right side. That is not good. Normally what we would do is we would increase the coefficient for our CO, then we would increase the coefficient for our C, but the CO needs to be a 1. Must be 1 for the coefficient. And so we need to adjust for the O2. Instead, we need to cut that number down. So we put a 1/2 in front of the O2 instead. So this would be our reaction, our formation reaction for carbon monoxide. And the delta H value that we have here, we would find from a table. We can't calculate that. We would just find it in a table. Some other examples. We want to write equations for the formation of sodium chloride and lead 2 nitrate from their elements in standard states, and we want to include the values of the standard heat of formation for each equation. The arrows here are showing which way you have to go to get to the table. So we saw sodium chloride before. I believe it was negative 411.2 with units of kilojoules per mole. For sodium chloride, what elements do we have in NaCl? We've got sodium. What else do we have? Chlorine. So we've got sodium and chlorine. We need to use them in their standard state forms. So I'm going to jump us back to the table that hopefully has these in there. So sodium and chlorine. We've got sodium as a solid. This is the one that's got the 0, so sodium as a solid is going to be our form for sodium. For chlorine, the one with a 0 is Cl2 as a gas. So if we didn't remember that horses need oats for clear brown eyes, or Brinkelhoff, or H7, or whatever mnemonic device for our diatomic elements, we would find it in our table. Cl2 has a standard heat of formation of 0. So Cl2 is going to be the one that we're going to write in. So let's go make those changes. So for sodium, it's as a solid. For chlorine, it's got a subscript of 2, and it's a gas. So now we've got standard states for our reactants. Is it balanced? It's not balanced. What do we need to do to get it balanced? Multiply chlorine by 1/2. That's exactly right. So we put a 1/2 in front of chlorine because our sodium chloride has to have the invisible coefficient of 1. And now it's balanced. We can add in our standard heat of formation that we got from the table, like so. And then for our lead 2 nitrate, we've got PbNO3 as a solid. What elements do we have here? We've got lead, we've got nitrogen, we've got oxygen. We need to put those into their standard states. So peeking ahead. This table has a couple of different values. We've got the delta H, we've got delta G, we've got a standard value for S. We're just going to be focused on the first column. So our lead has a 0 for its standard heat of formation when it's a solid, just by itself. And nitrogen and oxygen would have shown up in the previous table as gases, and they're diatomic. So subscripts of 2 and a little g behind them. So that gets everything into their standard states. And then we need to get it balanced. We've got lead 1 and 1 on both sides. Nitrogen, we've got 2 on the left. We've got 1 per nitrate, and we've got 2 nitrates, so that's 2 nitrogens. For oxygen, we've got 2 on the left, 3 times 2 on the right, so we need a coefficient of 3 in front of our O2. That'll get our oxygens balanced. And then we need to go steal that standard heat of formation value from our table. It's negative 451.9. So we break it down into its elements, put the elements into their standard states, balance it so that the product has 1 for its coefficient, and then grab our delta H value from a table. All in all, not very exciting, not very fun. Question?
How would you know which delta H value you choose for the product?
For the product, there's only one. So for PbNO3, lead is our main element here. So we find the lead heading, and then we've got lots of different lead compounds. We picked the one, computer enhance. We picked the one that had the same formula, PbNO3. And we took the delta H because we haven't learned about Gibbs free energy, or I forget what S is. So we just pick the one that matches. Other questions? Cool. All right, so the reason that we're learning this standard enthalpy change for a reaction is so that we can calculate for a reaction. So our standard heat of formation corresponds to the formation of a compound from its constituent elements in their standard states. We went over that. The negative of the heat of formation corresponds to the decomposition. So whatever the value is that we find in the table, this is formation, making it from its standard elements. If you flip it, make it negative if it's positive, make it positive if it's negative, then this is for decomposition. So one of the things that we were talking about at the start of the lecture relating to Hess's law, if you flip the left side and the right side for a delta H reaction, it flips the sign for your delta H value. And we can use this to calculate enthalpy changes for reactions. So any reaction can be written as the sum of formation reactions for our reactants and products. Sometimes they're going to be in their standard states, and so the values are 0, which makes the math really nice and easy. The standard heat of the reaction is the sum of the standard heat of formation values for the reactions, the products and the reactants. So we're using some sigma notation. The sigma is the weird looking E. It means sum. So we're adding up a bunch of things. So we're adding up the coefficient times the standard heat of formation for one of our products, plus the coefficient times the standard heat of formation of another product, plus the coefficient times the standard heat of formation of whatever other products we have, as many of those as we have. So adding all of those up, we'll get one number out from that, and then we're going to subtract our sum for our products. So coefficient times delta H plus, I'm lazy so I'm going to copy paste it, plus dot dot dot. This is the products. And then subtract from that the same thing, but for reactants. Products minus reactants for our delta H values. And if we do this, we'll get the delta H, the standard delta H for the reaction, the standard heat of the reaction. Let's look at an example. So we've got this big reaction. We want to calculate what's the standard delta H. What's the standard heat of the reaction? So we need to take our products, find their delta H values, subtract from that the reactants, their delta H values. So we would go to a table and we would look up our CO2 delta H of formation, our H2O standard heat of formation, and our methane standard heat of formation. We've got those all written out here. So for our products, we've got CO2, we've got one of them, our delta H is this value, negative 393.5. We're going to add to that our other product times its coefficient. It's got a coefficient of 2. So plus 2 times our delta H for water, negative 241.8. This is our sum of our products. And then we're going to subtract from that our delta H for our methane. Which is negative 74.6 kilojoules per mole. So for our products, the total is negative 877.1 kilojoules. And because this is a negative and we're subtracting it, it turns into a positive. So we're adding 74.6 kilojoules. So our overall delta H for the reaction is negative 802.5 kilojoules. And we can do an example for this. So we're going to have to reference back to our previous slides to find some of these delta H values. So we're looking for aluminum, iron 3 oxide, aluminum oxide, and iron. 2 of these are in their standard states though, so we don't have to look for them. Which 2 are those? The aluminum by itself and the iron by itself. And since those are in their standard states, that means that their standard heat of formation is going to be 0, so we can just ignore them. So we're really just looking for our iron 3 oxide, our rust, and our aluminum oxide. So let's go back and find those. I've got them with the green arrows. So there's our iron oxide, negative 824.2, and our aluminum oxide, negative 1,675.7. We'll have a little boomer moment where I'm taking a picture of my iPad. It always makes me feel extra old when I do stuff like that. Not quite as bad as taking a picture of something with my iPad, though. That really makes me feel old. Okay. Now we have to use those delta H values. What are we subtracting by what? Which side are we subtracting by which side? Products minus reactants. Products minus reactants. What is our product? The Al2O3, our aluminum oxide. And our value for our aluminum oxide is negative this big old number. And we're subtracting from that our reactant. They both have coefficients of 1, so we don't have to do any multiplication, and we only have one thing, so we don't actually have to add anything together. So we take our value for our iron 3 oxide, our Fe2O3. It was negative 824.2 kilojoules. So we're just using the number that we got from the table. We'll write them in here in green. So the negative with the negative means we're adding instead of subtracting. So negative 1,675.7 plus 824.2. Our delta H, standard delta H for the reaction is negative 851.5 kilojoules per mole. I think that these are relatively easy. The big part really is remembering that it's products minus reactants, and we're not doing anything fancy with it. We're not pre-swapping the value to be negative. We're just using the number that we found, all the products, add them up, subtract, all the reactants added up. Again, the big thing to remember is it's products minus reactants. We can also add on an extra step or extra steps. For example, chemical hand warmers produce heat. When they're removed from their airtight plastic wrappers, oxygen in the air reacts with the iron filings that are in the little pouch, and it makes rust. We want to calculate the standard heat of the reaction for this reaction and calculate how much heat is produced from a hand warmer that has 15 grams of iron powder in it. Assume all 15 grams react. So we need to calculate our standard heat of the reaction. How are we going to do that? Yeah, subtracting reactants from products, or products minus reactants. So we can go visit a table to find these values. Our Fe2O3 is negative 824.2 for its standard value. I'm going to take us back to the table. Let's look up Fe and O2. I think we're using both the tables. Fe iron, it's as a solid. Look at that, the delta H of 0. Very convenient. And then we'll go back to the other table that has our oxygen in it. We've got oxygen. We had O2 as a gas, and it's got a value of 0, which is very convenient. So we've got values of 0 and 0, also with units of kilojoules per mole. So what is our delta H for the reaction going to be? We have to double the 824. So we have to do the coefficient times the delta H value. So it's negative 2 times negative 824.4.2 kilojoules per mole minus the values for our reactants, 3 times 0 and 4 times 0. Which hopefully we know is going to be 0. So we're subtracting 0. So it's basically just this left side. 2 times negative 824.2. So our delta H, standard heat of the reaction, negative 1648.4 kilojoules per mole. And then we can also calculate the heat produced if we've got 15 grams of iron powder. So starting with our 15 grams of iron, iron being Fe, we need to convert from grams of iron to moles of iron so that we can use our balanced chemical reaction. Our value for molar mass for iron is 55.85 grams of iron per 1 mole of iron. So our grams of iron cancel. We want to go from moles of iron to heat in kilojoules. So we are going to be using blue underline, the two things we care about, 4 iron in, 4 moles of iron in, and this much kilojoules out. We're setting those two things equal to each other. So 4 moles Fe equals negative 1648.4 kilojoules per mole. And we can use this as a conversion factor. We need our moles of iron to cancel. We've got moles of iron on the top. So we're putting the 4 moles of iron on the bottom. And the heat part goes on top. Leave off the per mole here because it's per 4 moles of Fe. So 15 divided by 55.85 times negative 1648.4 divided by 4. This would produce 111 kilojoules of heat. Or negative 111 is what we get. So it produces / emits 111 kilojoules. Produces and emits are both words that indicate that this is heat lost, so it would be talking about a negative sign. And we're done with Chapter 7.